For the electrical team, we're primarily focused on the drive control and the arm control. This year, for the drive control, we're using 24-volt DC motors, as well as the Talon SRX motor controllers, along with an Arduino Mega in order to control our Rover, and in order to control the drive control. For the arm, we're using NEMA 23 stepper motors, as well as the DM542T stepper motor controllers, as well as an Arduino Uno in order to control the arm and its movement.
The programming team works together to develop necessary programs and packages for ROS, or the Robotic Operating System, which is the foundation of our code. On board the Rover, we have an NVIDIA Jetson Nano, which, alongside an array of sensors, handles important processes for autonomous navigation, such as computer vision and simultaneous localization and mapping. Over a pair of Ubiquiti Rocket M2 antennas, this board talks to our base station machine, where we send out controls, receive data, and monitor our systems over a custom GUI. In order to increase our ability to adapt to changing conditions with the pandemic, we began diving deeper into robot simulation this year using a platform called Webots. Using the simulator will enable us to prototype our code more efficiently and safely, both in person and from home. Simulation will also be an important part of developing the inverse kinematics that will control the arm mechanism.
This past year, the mechanical team has overhauled many components of the Rover, including the chassis, rocker bogie, and the manipulator. The chassis of the Rover has been redesigned using knowledge and experience gained from Ad Astra. This year, the chassis sports a frame made from T-slot aluminum extrusion to provide a solid structure for the manipulator and science module to be mounted to. The chassis is being kept level through the use of a bar differential just like in previous years. Our Rover, mounted on the rocker bogie, is the drive system, which consists of 6 chain-driven wheels. These wheels have been 3D printed out of a flexible material called TPU, meaning our wheels consist only of a single part instead of being a complex assembly like in years past.
This year we have fully redesigned our manipulator. The intent behind this was to reduce the amount of play in the end effector. Our manipulator has 6 degrees of freedom, many of which are being driven through a timing pulley or a lead screw, allowing for the precise positioning of the arm. The end effector design is modified 4-bar mechanism driven by a lead screw and features semi-flexible grip printed out of TPU.
The Science Task module features a pulley-driven auger system, which will collect soil samples from a site of interest. The soil is deposited into a collection tray, where it will be mixed with water and analyzed for key organic compounds such as sulfate, nitrate, and ammonia, as well as for pH. Once analyzed, the soil solution is safely stored in a waste collection unit on board the Rover. In addition, the module is capable of detecting environmental readings such as temperature, humidity, and atmospheric pressure, allowing us to better understand the habitability of a test site.